Hello all, and welcome to the next installment in my algebra series. In this video, we're going to talk about something that we've already talked about, graphing functions. And we've talked about a number of different ways to graph functions already. Um, Not very sophisticated, but the first method was plotting points. Remember, the graph is made up of individual points. So one way to make a picture of the graph is to plug in a value for x and figure out a value for y. That's 1 point. And then do it again. Evaluate the function, right? Plug in a second x value, get a second y value. And once you have 5 points or 10 points or 20 or 50, depending on how complicated the function is, you're basically going to have a graph and you plot a point and you plot another point and then another point and then maybe another point right here and another point over here. And then eventually you plot enough points to where you say, okay, well, this is starting to look like something like this. Okay, so plotting points. Now, we've also talked about using technology, plugging or typing this function in. So let's say, for example, you want to graph this guy right here. Now, you could type that into a graphing calculator. You could type that into Desmos or some other graphing utility. But the method, so this is, let's say method 3, the method that we're going to be using, or what are called graph transformations. Right, graph transformation. So let's say the goal here, we want to graph the function. Right, we want to graph this guy. F of x equals -4 times parentheses x minus 3 close parentheses squared plus 7. Right, so to graph this function, f of x, the method of transformation, graph transformations, is to do this. Right, start with the graph of the simplest version of this type of function. This is a squared function. You're saying x is being squared. Right? There's some addition and some subtraction, some multiplication, but we see a second power. So this is some more complicated version of y equals x squared. So we start with the simplest version of this type or this family of functions. Well, so the first thing we need to know what x squared looks like, and hopefully we do, because this is something that we've seen. It's a parabola, so it goes up, up. It's not. I didn't draw it exactly symmetric, but it should look symmetric. So maybe I'll make it look a little. Yeah, hard to make it look perfect, but something like that. All right, so this is the graph of y equals x squared. And using graph transformations, we're going to take this green one, this green parabola, and maybe we'll move it left, right, up, down. So that's one type of transformation. Move left, right, up, or down. That's a result of addition or subtraction. That's a result of addition or subtraction. So if you see this green function at the top, f of x, if you see f of x, well, we've got addition right there, plus 7. We've got subtraction right there, a minus 3. Right? The minus 4, that's multiplication. But we have one addition and we have one subtraction. All right, so that's going to result in taking that green graph of x squared and moving it somehow. Haven't talked about how, but we will. We will. Okay. The second type of transformation is reflections. So we've talked about reflections previously already when we talked about symmetry in equations, x-axis symmetry, y-axis symmetry, and origin symmetry. So you could reflect vertically or horizontally. Right, functions could be even or odd. So we've already talked about reflecting the graphs of functions. And you do this, you reflect or flip the graph vertically or horizontally as a result of negative signs. Okay, see a negative sign in the original function right here in front. I just highlighted yellow. So there's a negative sign, so it might be some sort of reflecting going on. And then the third type of graph transformation, we'll say number 3, is you could stretch or compress the graph. Vertically or horizontally. So we'll talk about each one of these one by one. Stretching and compressing, either in the vertical or horizontal direction, that comes as a result of multiplication. Multiplication or division. So what we want to do is to graph this more complicated x squared version of an x squared function, we want to start with the simplest version, right? We want to move it left, right, up, down. We want to reflect it possibly over the x-axis, over the y-axis. We want to maybe stretch it, make it skinnier, make it wider, right? Or some combination of these. And then we should end up with the graph of f of x equals -4 times parentheses x minus 3 squared, close parentheses, plus 7. Okay, so let's see how this works. Well, the first thing and most important thing is, do you know these graphs? Like the simplest version of the x squared family of functions, the simplest version of a absolute value function, the simplest version of a square root function. So that's where we got to start, making sure we're clear, right? We're clear on the starting point in each problem. So my slideshow starts off with graphs of common functions. So the function here is the constant function. F of x equals c, where c is any number, right? So f of x equals 7, f of x equals -12, f of x equals 2.261, f of x equals pi, f of x equals a number. Now, the shape of all of those graphs is the same. It's a horizontal line, right? The shape. So we're talking about like the shape of what a constant function looks like. This is f of x equals c. They're all going to be some version of a horizontal line. It might be down, might be up, but it's always a horizontal line. Then we've got what's called the identity function, or y equals x, right? So y equals mx plus b is a more complicated version of this function. They are all straight lines. Anytime the highest power of x is 1, it's just x to the first power, you get a constant function. Sorry, not constant function. You get a constant slope. So you get some version of a straight line. We've got the absolute value graph. Right? So this is the simplest version of an absolute value function. It could get more complicated from there, and the graph is this V shape. Right? The graph is this V shape. So right now we're just going through, and we've seen all of these before. We're just now putting them all together in one place. So like for example, like the problem would be like graph the function. Let's say you might see graph the function g of x. Let's say g of x this time equals -1/2 times the absolute value of x minus 3 plus 1, right? This would be a more complicated version of the absolute value graph. So you would start with this. This is where you start the problem. Right? This is the problem. Graph this function. This is where you would start. We've got this is the simplest version of the x squared graph. Oh, didn't want to use a pen there. I wanted to use a highlighter. That's better. All right, so this is the simplest version of the x squared graph. It's a parabola, sort of centered here at the origin, so that point where the x-axis and the y-axis cross. Right here, that's the origin, or the point 0, 0. We've got the square root function. Right, so any version of a function that includes the square root of x somehow. Right? This is our starting point. This graph right here. Just it's always a good idea to identify like a nice convenient point to work with. So if we need to move the graph, we can move this one point, and the rest of the graph will follow. And so there's the origin again, 0, 0. We got x cubed. So the graph of x cubed, well, it's basically looks like, not exactly technically, but it looks like you take half of a parabola, right, and you reflect that down. So the left half, instead of going up like this, it's going down. So the right side of the parabola goes up, the left side goes down. It's not exactly a parabola, but it has that same general appearance, let's say. And so if the problem said graph the function, graph f of x equals negative 3 minus x to the third power plus 1, something like that. Well, we see an x cubed, so we would start with this graph. We would start with this graph. And then we would change this graph somehow. Flip it, move it, stretch it, compress it. We would do something. Okay, so now let's get to an actual problem. All right, so if the problem you're trying to graph is the cube root function, this is the graph of the cube root of x. It looks just like the square root of x, except instead of going only to the right from the origin, it's going in both directions. Because you can actually take the cube root. You can take the cube root of a negative number. And this graph goes through the origin again. That would be 0, 0. Okay, so let's sort of piece this together one transformation at a time. I think that makes sense. So let's start with, here's our problem. Graph this function. Graph this function. Now over here on the right, I have the graph of, this red graph is y equals the square root of x, and this actually keeps going forever. And this is the point right here. This is the point 0, 0. So we want to graph g of x, which is the square root. So this one right here, we want to graph the square root of x plus 5. So what does the plus 5 do? And that's what it comes down to with these graph transformations. Now you don't have just x, you have some numbers involved with the x, some addition, subtraction, multiplication, or division, maybe some negative signs. So to graph this g of x, the question is, what does the plus 5 do? What does the plus 5 do? Well, addition or subtraction can happen a couple of different ways. Each one could happen a couple of different ways. So before we graph this one, let me give you an example of each. So down here in this table, where you see f of x plus c, f of x minus c, then you see f of x plus c and f of x minus c. So I'm looking right here. So let's call this 1, 2, 3, and 4. We've got 4 cases because there's 4 directions you can move. Remember, shifting or moving the graph is a result of addition and subtraction. All right, so you could move the graph up, you can move it down, you can move it, this direction, this direction, this direction, or this direction, right? Let me switch to a different color. So moving the graph to the left, this is number 1 in this table, is a result of adding a number inside with the function. Adding a number inside with the function. So see how I just highlighted the x plus c in the parentheses? That would be, for example, g of x is equal to the square root of x plus 5, with the plus 5 inside with the square root function. So here, the function we're working with is the square root function. And when I'm referring to inside versus outside, like a plus 5 inside or a plus 5 outside, you're going to hear me referring to inside, outside. This is what I mean by outside. It's not being affected. The plus 5 is not being affected by the square root. And this is what I refer to as inside. The plus 5 is inside of the function. Okay, because this plus 5 here is being affected by the function. So if there's a plus 5 on the outside, it does one thing. A plus 5 on the inside, it does another thing. In this case, if there was a plus 5 on the inside, we would move the graph to the left. Right, this would tell us move left. You would move the graph left 5 units. So instead of the point 0, 0, it would actually be over here at negative 5, 0, and then the graph would go this way. But that's not what we have. That's not what we have. The second one. Subtraction on the inside. Subtraction on the inside would be something like g of x is equal to the square root of x minus, not 7, x minus 5. Again, the subtraction is on the inside because the function is affecting the number 5. It's inside of the square root. Anytime you have something going on, addition, subtraction, multiplication, division, inside of the function, that's happening in the x direction. It's happening to the x value first, before the function is taking place. So that would tell us to move the entire graph right 5 units. So the whole graph would shift over this way and start and be the same shape, but it would go to the right, starting at 5, positive 5 on the x-axis. That's not what we have. Then we've got the up and the down, right? The up and the down. Oh, it's not a highlighter. The up and the down, right? That's coming from addition and subtraction outside of the function. So that would look like, we're still doing, I'm using 5 as the example here, just as the example in this problem. G of x equals the square root of x with a plus 5. That is the problem here that we're trying to graph, right? So that's what I mean by outside of the function. There is a plus 5 on the outside. Right? The plus 5 is not being affected by the square root. And with the, let's go back up here. When you have a plus or a minus inside, you have to do the opposite. Always the opposite. Right? If in the first case, if there was a plus 5 inside with the x, you move in the negative direction, left. If there's a minus 5, you move in the positive direction. If we're looking down here, f of x is shifted up c units when you have a plus on the outside. In this case, the c is the 5. So you would move up 5 units. And then the last case, if you have a minus on the outside, a minus on the outside, so the 1, 2, 3, and 4 on this table on the bottom corresponds to the 1, 2, 3, 4 and what I'm writing up here. Square root of x minus 5 on the outside. So again, I'll write outside here. And when you have subtraction on the outside, you move vertically. In this case, we would move down, not up. So we'll say move down 5 units. So for this particular problem, there's a plus 5. So you have to just, go to this table and figure out, okay, which case are we working with? And that's actually case number 3. You have addition on the outside. Right? You've got addition on the outside. So that means you're moving the function up. And so what I said earlier, you pick a convenient point. Like, for example, the point 0, 0. And just move that point. So now we've got the point 0, 5. Plus 5 on the outside means the entire graph goes up 5. Move that first point up 5, and the rest of the graph you draw the exact same diagram as in red. So this green graph right here, that's the answer. This is really like a 30-second, 20, 30-second problem. I took 10 minutes to explain it because we're going to take this and apply it to every other problem. Anytime you see a plus or a minus with graph transformations, anytime you see a plus something or minus something, addition or subtraction, it means you take the starting graph and you move it either up or down or left or right. Okay, next one. We'll do this much quicker because we've already done the theory, the explanation. So we want to graph the function f of x equals the square root of x plus 6. We've got addition on the inside. We've got addition on the inside, so that looks like case number 1. You have a plus 6 inside of the square root function. So a plus on the inside means you move in the negative direction. The negative direction. So we're going to move 6 units to the left. So now that point started at 0, 0, and now we're at -6 on the x, 0 on the y, and we draw exact copy of the graph, just moved to the left. Okay, so that's it for number 2. Let's keep going, explore some of the other types of transformations. Okay, so now you see I've got 2 tables. I've got the one that we've just been discussing, the addition, subtraction, and now I've got reflections. Now reflections come from a negative sign, not subtraction. Right? This right here is not a negative sign. That's subtraction. So we just talked about what that does. A -3 on the inside, that's this case right here. A minus something on the inside is going to shift the graph right. And now we've got reflections. So we've taught when we were talking about symmetry of equations and even and odd functions, we talked about reflecting the graph over the x-axis. So the top of the graph reflects down to the bottom reflects to the top. When I say top, I'm talking about above the x-axis, and bottom is below the x-axis. So if we were to take this red graph over here, if we were going to take that graph and reflect it vertically, we would end up with that graph. That's a vertical reflection over the x-axis. If we were to reflect it horizontally, it would reflect left to right. It would go this way. All right, so that's how we're using reflections here. In this case, we've got h of x equals a negative on the outside of the square root. So outside of the function. So this example has two different transformations. We got to move the graph to the right, and we've got to reflect it vertically. All right, so this is a two-step problem. This is a two-step problem. So step 1, there's a shift to the right. -3 on the inside means we move over to a minus 3 units to the right, so that will be the point 3 for the x, comma 0 for the y. All right, let me use a different color. Actually, I'm going to change to blue. 1, 2, 3. That's right there. That's the point 3, comma 0. We started here at the point 0, comma 0. And then we draw the graph. Now that is the graph of y equals, or we could use another letter for the function. We call it j of x or p of x or m of x, but I'm just going to say y. Y equals the square root of x minus 3 without the negative sign, right? That's without the negative sign, just the -3 on the inside. And then step 2, reflect vertically. Step 2 is reflect vertically. So now this blue graph, I'll use green for the final answer. Now the blue graph is going to be reflected vertically or over the x-axis. So that green one is h of x equals negative square root x minus 3. And I'm going to erase the blue one because that's not part of the answer. That's our work, our scrap work. And our final answer is that green one. The red graph was shifted to the right and then reflected top to bottom.